What if the farthest human-made object ever launched into space is trying to tell us something, and we simply do not understand it? Out there, beyond the planets, beyond the orbit of Pluto, beyond even the invisible boundary where the sun's influence fades into the wider galaxy, a faint signal continues to arrive on Earth. It comes from Voyager 1, a machine launched in 1977, a relic of another era, a spacecraft older than most of the people listening out to this story. And yet, it is still speaking. But something about its voice has changed. According to NASA engineers, the transmission being received does not match what Voyager 1 should be capable of sending. The signal is real, the spacecraft is still responding, but the data does not make sense. It is as if the spacecraft is alive, functioning and communicating, but speaking in a language no one taught it. At first glance, this might sound like a simple technical malfunction. After all, Voyager 1 is ancient by modern standards. Its systems were designed decades before smartphones, before the internet as we know it, before most of modern computing. You would expect it to fail. You would expect it to go silent. But that's not what happened. Instead, it continued transmitting. Strong, consistent, structured. And yet the information inside those transmissions appears scrambled, distorted, or impossible. Bits of data that should correspond to known engineering values suddenly fall outside expected ranges. Telemetry that should describe temperature orientation and system health instead arrives in patterns that do not align with reality. And this is where the contradiction begins. Because if Voyager 1 were truly malfunctioning, its signal should degrade. It should weaken. It should become chaotic. But it has not. The signal remains stable, clear, intentional, which leads to a question that scientists did not expect to ask. How can a spacecraft send a perfect signal containing imperfect information? To understand why this is so unsettling, you have to imagine the scale of what Voyager 1 has accomplished. It has travelled farther than any object humanity has ever built. It has crossed distances so vast that its signals take more than 20 hours to reach Earth travelling at the speed of light. Every message we receive from it is a message from nearly a full day in the past. And still against all odds, it continues to respond. Every command sent from Earth is received. Every reply is returned. There is no silence. There is no disappearance. Only confusion. Inside mission control engineers began to notice subtle irregularities. At first, they were easy to dismiss. Small inconsistencies, slight deviations, the kind of noise you might expect from a machine operating billions of kilometers away in the cold vacuum of space. But over time, those inconsistencies grew. They became patterns that should not exist. According to reports from NASA's Jet Propulsion Laboratory, the spacecraft's attitude control system, which is responsible for keeping its antenna pointed toward Earth, appeared to be functioning perfectly. The antenna was aligned, the signal was strong, and yet the telemetry describing that system suggested something completely different. It was as if Voyager 1 was telling us two contradictory stories at the same time. One story said everything was working, the other said something was deeply wrong, and both stories were coming from the same source. This is where the mystery deepens, because in space exploration data is everything. Engineers rely on precise, consistent readings to understand what a spacecraft is doing. Every system, every component, every tiny movement is encoded into streams of numbers that can be interpreted back on Earth. When those numbers stop making sense, it is not just a technical issue. It is a breakdown in communication itself. Imagine speaking to someone on the phone, you can hear their voice clearly. The connection is perfect, but the words they are saying are scrambled, not random noise, not static, but structured sentences that somehow carry no meaning. That is what Voyager 1's transmission feels like to the scientists receiving it. A voice from the edge of the solar system, speaking clearly, but saying something we cannot understand. And the deeper scientists looked, the stranger it became, because the signal was not just noise. Yes. It was organized, consistent, repeating in ways that suggested intention or at least a system still following its internal logic. This ruled out many simple explanations. It was not just interference from cosmic radiation. It was not just a damaged antenna. It was not just a failing power supply. The spacecraft was behaving as if it were healthy, but reporting data as if it were not. This contradiction forced scientists into unfamiliar territory. They had to consider the possibility that the problem was not just inside the spacecraft, but in the environment surrounding it, because Voyager 1 is no longer in the region of space where it was designed to operate. It has left the protective bubble of the Sun. It's now travelling through interstellar space, a place we do not fully understand, a place where the rules may not behave exactly as we expect. And this is where the mystery transforms into something much larger. Because if the environment beyond the solar system can alter how a spacecraft communicates, if it can distort data without weakening the signal, then Voyager 1 is not just malfunctioning. It is revealing something new, something we did not predict, something we did not prepare for. For decades, scientists believed they understood the boundary between our solar system and the rest of the galaxy. They believed they understood how particles, magnetic fields, and radiation would behave beyond that boundary. Voyager 1 was supposed to confirm those models, to validate them, to provide clean, predictable data. Instead, it has done something else entirely. It has introduced uncertainty. And in science, uncertainty is where discovery begins. Because every time reality refuses to match our expectations, it forces us to look deeper, to question assumptions, to explore possibilities that once seemed unnecessary. And right now, Voyager 1 is doing exactly that. It is challenging our understanding of interstellar space, not through silence, but through a message we cannot yet decode, a message that continues to arrive hour after hour, day after day across billions of kilometers of empty space, still speaking, still transmitting, still not making sense. And the most unsettling part is this. We are not entirely sure whether the problem is in the spacecraft or in the space around it. Because if the signal itself is perfect, then something else must be changing the meaning of what is being sent. Something invisible, something we have never directly experienced before. Something waiting, just beyond the edge of everything we thought we knew. And that raises a question scientists are only beginning to confront. What exactly did Voyager 1 encounter when it left our solar system? To understand why this signal is so deeply unsettling, you have to step back and follow the journey that brought Voyager 1 to the edge of everything we call home. Because Voyager 1 was never meant to be here. When it launched in 1977, its mission was ambitious, but not infinite. According to NASA, the goal was to take advantage of a rare planetary alignment, a once-in-nearly-2 centuries opportunity that would allow a spacecraft to visit multiple outer planets using gravitational assists. Jupiter, Saturn, possibly beyond. At the time, even reaching those worlds was considered extraordinary. No one expected Voyager 1 to become humanity's first interstellar messenger, and yet that is exactly what happened. After its launch from Cape Canaveral, Voyager 1 began accelerating outward, using the immense gravity of Jupiter to slingshot itself towards Saturn. This maneuver was not just a shortcut, it was a carefully calculated transfer of energy, allowing the spacecraft to gain speed without using additional fuel. And it worked perfectly. Voyager 1 flew past Jupiter in 1979, capturing images of swirling storms, volcanic eruptions on the Moon Io, and details that fundamentally changed our understanding of the gas giant system. Then it moved on, towards Saturn. In 1980, Voyager 1 made its historic flyby, sending back detailed observations of the planet's rings and its largest moon Titan. But this encounter came with a decision. A turning point. Scientists chose to direct Voyager 1 toward Titan for a closer look, knowing that doing so would alter its trajectory permanently. It would no longer continue along the plane of the solar system. It would be ejected upward, out of the planetary disk and into deep space. At the time, this was a trade-off, a sacrifice of future planetary encounters in exchange for unprecedented data about one mysterious moon. No one knew that this decision would send Voyager 1 on a path no spacecraft had ever taken before. A path out beyond Saturn. Voyager 1 did not slow down. It kept going, faster than any human-made object had ever travelled. And as the years passed, something remarkable happened. It did not stop working. Decade after decade, the spacecraft continued to transmit data. Its systems aged, its power slowly declined, as its plutonium fuel decayed, but its core instruments kept functioning. carefully managed by engineers at NASA's Jet Propulsion Laboratory, Voyager 1 became a long-term experiment in endurance. How far could a machine built on Earth survive? How long could it keep speaking? By the early 2000s, Voyager 1 was approaching a region scientists had theorized about for decades. The boundary of the Sun's influence. Known as the heliosphere, this vast bubble is created by the solar wind, a continuous stream of charged particles flowing outward from the Sun. It extends far beyond the planets, forming a protective shield against cosmic radiation from the galaxy. Inside this bubble, the environment is dominated by the Sun. Outside it, the galaxy takes over. For years, scientists debated where exactly this boundary lay. It was not a sharp line. It was more like a transition zone where solar particles gradually give way to interstellar particles and magnetic fields begin to shift. Voyager 1 was heading straight into it. And this is where the story becomes even more fascinating. Because as Voyager 1 approached this boundary, its instruments began detecting subtle changes. The solar wind was slowing. The density of charged particles was increasing. Magnetic field orientations began to fluctuate. These were the first hints that the spacecraft was nearing something significant, something no human-made object had ever experienced. Then in 2012 it happened. According to NASA, Voyager 1 crossed into interstellar space. It became the first object ever to leave the heliosphere and enter the space between stars. But even this moment was not as simple as it sounds, because scientists did not immediately realize it had happened. There was no sudden drop in signal, no dramatic change, no clear boundary. Instead, the evidence came from indirect measurements. One of the key indicators was a sharp increase in cosmic rays. These high-energy particles originating from distant stars and supernovae are usually deflected by the heliosphere, but beyond it their intensity rises. Voyager 1 detected exactly that. At the same time, the solar wind effectively disappeared. The spacecraft was no longer surrounded by particles from our Sun. It was immersed in the interstellar medium. And yet, something did not quite match expectations. The magnetic field did not shift as dramatically as predicted. Scientists had expected a clear change in direction, a signature that would mark the crossing of the heliopause, the outer boundary of the heliosphere. But Voyager 1's data suggested something more complex, a smoother transition, a blending of environments. This was the first hint that interstellar space might not behave the way we thought, and it would not be the last. Because as Voyager 1 continued its journey deeper into the unknown, it began to encounter conditions no spacecraft had ever measured directly. Extremely low densities of matter, weak but persistent magnetic fields, regions of plasma that behaved in unexpected ways, and all the while it kept transmitting, sending back data across billions of kilometers, data that scientists carefully analyzed, compared and debated. For years, Voyager 1 was a triumph of engineering and science, a confirmation of theories, a validation of decades of research. It was doing exactly what it was supposed to do, until it wasn't. Because somewhere along that endless journey something changed. Not in a dramatic obvious way, but quietly, subtly. The kind of change that only becomes visible when you look closely enough. At first, the anomalies were easy to dismiss. A few strange readings, minor inconsistencies, but Voyager 1 had already survived for decades. It had endured radiation, extreme cold, and the gradual decay of its own power source. Small errors were expected. What was not expected was consistency within those errors, because over time the anomalies began to repeat, patterns began to form, and those patterns suggested something deeper, something systematic, something that could not be explained by simple wear and tear. This is when engineers and scientists began to pay closer attention, because Voyager 1 was no longer just a spacecraft exploring interstellar space. It had become something else, a probe not just of distance, but of the unknown behavior of the universe itself. And the signal it was sending, that strange, contradictory transmission, may have been the first real clue that interstellar space is not as empty or as simple as we once believed. Because if everything we thought we knew about this region was correct, then Voyager 1's data should have made perfect sense. But it didn't. And that raises a deeper question. If our models of interstellar space were incomplete, then what exactly is Voyager 1 moving through right now? For decades, long before Voyager 1 ever reached the edge of the solar system, scientists believed they already understood what lay beyond. Not in detail, but in principle. The region outside the sun's protective bubble was thought to be simple, quiet, almost empty. According to the models developed throughout the late 20th century, interstellar space was expected to be a thin, cold environment filled with sparse gas, mostly hydrogen drifting between the stars. Magnetic fields would exist, but they would be weak and relatively uniform. Radiation would increase, but in predictable ways. Nothing chaotic. Nothing structured enough to interfere with a spacecraft's internal systems. Nothing that could distort a signal without weakening it. In fact, if you asked most scientists at the time, they would have told you that interstellar space was one of the most stable environments imaginable, and that assumption shaped everything about Voyager 1's design. Engineers at NASA and the Jet Propulsion Laboratory built the spacecraft to survive planetary flybys, radiation belts, and the gradual decline of power over time. But they did not design it to encounter something fundamentally unknown, because nothing in the models suggested that would happen. The heliosphere itself, the vast bubble created by the solar wind, was understood as a kind of boundary layer. Inside it the sun dominates. Outside it the galaxy takes over. The transition between the two was expected to be gradual but ultimately predictable. Scientists use terms like heliopause and termination shock to describe these regions, mapping them in theoretical models long before any spacecraft could reach them. And according to those models, once Voyager 1 crossed the heliopause, its environment would become simpler, not more complex. The solar wind would fade. Interstellar particles would dominate. Magnetic fields would shift into alignment with the broader structure of the galaxy. Everything would follow a clean, understandable pattern. That was the expectation, and for a time it seemed to be correct. When Voyager 1 began detecting increased levels of cosmic rays and a decline in solar particles, scientists were confident that it was approaching the boundary they had predicted. These observations matched decades of theoretical work. They reinforced the idea that our understanding of the heliosphere was accurate. Even when the spacecraft officially crossed into interstellar space in 2012, the data largely confirmed what scientists had anticipated, at least on the surface. But beneath that confirmation there were subtle inconsistencies, small deviations that did not quite fit. For example, the magnetic field direction did not change as sharply as expected. Instead of a clear boundary, there appeared to be a region of overlap where solar and interstellar influences coexisted in a more complex structure. At the time, this was considered an interesting detail, not a contradiction, not a problem, just a refinement of the model. And that is how science often progresses. Theories are adjusted, parameters are updated, new data is incorporated into existing frameworks. But what Voyager 1 would eventually reveal was not a small refinement. It was something much more disruptive, because the models did not just describe the environment, they also predicted how that environment would affect the spacecraft. Signals, for example, were expected to behave in very specific ways. Radio waves, the kind Voyager 1 uses to communicate with Earth, travel through space with minimal interference. Even over billions of kilometers, they should remain stable as long as the transmitter and receiver are functioning properly. Interstellar plasma, the thin ionized gas between stars, could cause slight delays or distortions, but nothing dramatic. Nothing that would scramble structured data while leaving the signal itself intact. That was the key assumption. If a signal arrived clearly, then the information inside it should also be clear. And if the information was corrupted, then the signal itself should show signs of degradation. There should be a direct relationship between the two. But Voyager 1 broke that relationship. It began sending signals that were clean, but filled with data that did not correspond to reality. And according to everything scientists believed at the time, that should not be possible. This is where the old models began to show their limits, because they were built on indirect observations. Before Voyager 1, no spacecraft had ever entered interstellar space. Everything we thought we knew about that region came from telescopes, theoretical physics, and simulations. We were, in a sense, guessing. Educated guesses supported by evidence but still incomplete. Voyager 1 was supposed to provide confirmation. Instead, it provided contradiction. And that contradiction forced scientists to reconsider something fundamental. What if interstellar space is not as uniform as we thought? What if it contains structures, fluctuations, or interactions that we have not yet fully understood? Because if such structures exist, they could potentially influence how signals propagate. They could alter the behavior of charged particles. They could even interact with a spacecraft's systems in ways that were never anticipated. At this point, it is important to understand just how delicate Voyager 1's communication system is. The spacecraft transmits with only about 20 watts of power, roughly the same as a dim light bulb. And yet that signal travels across billions of kilometers and is still detectable by the Deep Space Network on Earth. This is possible because the signal is highly focused, and because space in theory offers very little resistance. But what if that theory is incomplete? What if the space Voyager 1 is travelling through is not truly empty? What if it contains variations in density, magnetic turbulence, or plasma waves that can subtly influence the signal, not enough to weaken it, but enough to change the information it carries? This idea was not part of the original models. It was not something engineers designed for, because there was no reason to, until now. As the anomalies in Voyager 1's data became more persistent, scientists began to realize that they might not be dealing with a simple onboard malfunction. They might be observing the effects of an environment that behaves differently than expected. An environment that does not just passively exist, but actively interacts. And that realization changes everything. Because it means that Voyager 1 is not just sending us information about itself. It is sending us information about the space around it, even if we do not yet know how to interpret it. And that brings us to a critical turning point in this story. Because once scientists accepted that their models might be incomplete, they had to confront a much more difficult question. If the old assumptions were wrong, then what else might we have misunderstood about the boundary between our solar system and the galaxy beyond? At first, it did not look like a mystery. It looked like noise. The engineers monitoring Voyager 1 were used to imperfections. After decades in space, small glitches were expected. A flipped bit here, a delayed response there. These were the normal signs of an aging spacecraft operating far beyond its original lifespan. So when the first irregular readings appeared, they did not trigger alarm. They triggered routine checks. According to NASA, the anomalies began as subtle inconsistencies in telemetry data. Values that should have remained within strict ranges occasionally drifted outside them. Temperatures that did not match known conditions. Orientation data that did not align with the spacecraft's actual position. Nothing dramatic, nothing catastrophic. Just wrong. At first, engineers assumed a simple explanation. Radiation. High-energy particles in deep space are known to interfere with electronics, occasionally flipping bits in memory or causing temporary malfunctions. Voyager 1 had encountered radiation before, especially during its early flybys of Jupiter and Saturn. So the team checked for patterns consistent with radiation events. But the data did not behave like radiation noise. Radiation errors are typically random. They appear suddenly and then disappear, leaving no consistent structure behind. Voyager 1's anomalies were different. They repeated. The same incorrect values appeared again and again, as if the spacecraft was following a set of instructions that no longer matched reality. This was the first sign that something deeper was happening. Because repetition implies system behavior, not randomness. Engineers began to isolate specific subsystems to determine where the problem might be originating. One of the primary areas of concern was the attitude, articulation, and control system. This system is responsible for keeping Voyager 1's antenna pointed precisely at Earth. Even a small misalignment would weaken the signal significantly, but the signal strength remained strong. Consistent, exactly as expected, which meant the spacecraft was oriented correctly, and yet the telemetry describing that orientation suggested otherwise. It reported values that did not make sense, values that implied the spacecraft was pointing in the wrong direction, even though the signal proved it was not. This contradiction forced engineers to consider a more complex scenario. What if the spacecraft was functioning correctly, but reporting incorrectly? In other words, what if the problem was not in the physical systems, but in the data being generated or transmitted? This led to a deeper investigation into Voyager 1's onboard computer systems. Unlike modern spacecraft, Voyager 1 does not have a single unified computer. It has multiple subsystems, each responsible for different functions. These include the flight data subsystem, which formats and sends telemetry back to Earth, and the attitude control system, which manages orientation. If the Voyager data subsystem were compromised, it could potentially send incorrect information even if the underlying systems were operating normally. So engineers began testing that hypothesis. They sent commands. They requested specific data. They compared responses over time, and what they found only made the situation more confusing. Because the spacecraft responded correctly to commands, it acknowledged instruction, it executed them, it behaved as if its internal logic was intact. But the data it returned still did not align with reality. It was as if the spacecraft understood what it was being asked to do, but could not accurately describe what it was doing. And this is where the problem became truly unusual. Because in most cases, hardware failures produce clear symptoms. A sensor fails and its readings go to zero or fluctuate wildly. A communication system degrades and the signal becomes weak or distorted. A power issue arises and systems begin to shut down. But Voyager 1 was not showing any of those signs. It was stable, operational, responsive, and yet inconsistent. Engineers at NASA's Jet Propulsion Laboratory began to suspect that the issue might lie in the way data was being encoded before transmission. Voyager 1's telemetry is not sent as raw information. It is processed, formatted, and packaged into a specific structure that can be decoded on Earth. If something in that formatting process were malfunctioning, it could produce data that appears valid on the surface but does not correspond to actual conditions. So the team examined the formatting system. They analysed the patterns in the corrupted data. They looked for signs of memory errors, timing issues, or software faults. And once again, they found something unexpected. The data was not random. It followed consistent patterns. Patterns that suggested the system was still operating according to its internal rules. But those rules no longer produced correct outputs. This is the kind of problem that engineers rarely encounter. A system that is both functional and incorrect at the same time. A system that obeys its design, but yields results that defy interpretation. At this point, the investigation reached a critical stage. Because the usual troubleshooting methods were not working, there was no clear component to replace, no obvious fault to isolate. And Voyager 1 is far beyond any possibility of physical repair. Every solution had to be implemented remotely through commands sent across billions of kilometers with a delay of more than 20 hours each way. This meant that every test took nearly 2 days to complete. Every hypothesis required patience, and every mistake could cost valuable time. Despite these challenges, engineers continued to probe the system. They began sending carefully crafted commands designed to test specific parts of the spacecraft's memory and processing units. They attempted to reroute data, to bypass suspected faulty regions, to isolate the source of the inconsistency. And slowly, piece by piece, a new picture began to emerge. The problem did not appear to be a total system failure. It looked more like a localized issue, something affecting how certain data was being generated or interpreted. But even this explanation did not fully resolve the mystery, because the nature of the corruption did not match any known failure mode. It was too structured, too consistent, too deliberate in a sense. Not intentional, but systematic. And that raised a question that engineers were not comfortable asking. What if the problem was not entirely inside the spacecraft? What if something external was influencing how its systems behaved? Because Voyager 1 was now in an environment unlike any it had encountered before. An environment that was not fully understood. An environment that might interact with electronic signals or data in ways we had never directly observed. This idea was not the first explanation. It was the last. The one you consider when all conventional possibilities have been exhausted. And yet as the investigation continued, it became harder to ignore, because every internal explanation seemed incomplete. Every hardware theory left gaps. Every software hypothesis failed to account for the consistency of the anomalies. Something did not fit. And when something does not fit in science, it often means one of two things. Either we have made a mistake, or we have discovered something new. And Voyager 1, drifting alone in the darkness beyond the solar system, was beginning to suggest that the answer might not be as simple as a malfunction. Because if the spacecraft itself was not entirely to blame, then something else must be shaping the signal. Something we cannot see. Something we have not yet fully understood. And that possibility leads to a far more unsettling question. What exactly did Voyager 1 cross when it left the sun behind. There is no line in space, no glowing boundary, no sudden wall where one region ends and another begins. And yet somewhere far beyond the orbit of Neptune, beyond Pluto, beyond the Kuiper belt, there exists a transition so profound that it separates everything influenced by our sun from everything beyond it. This boundary is known as the heliopause. And when Voyager 1 reached it, scientists expected clarity. They expected confirmation. Instead, they found ambiguity. To understand why, you have to imagine the solar system not as a collection of planets, but as a bubble, a vast invisible bubble carved into the galaxy by the solar wind. The sun is constantly emitting a stream of charged particles flowing outward in all directions at incredible speeds. This stream creates pressure pushing against the interstellar medium, the thin gas and plasma that fills the space between stars. Where these two forces meet, a boundary forms. Inside the bubble, the sun dominates. Outside, the galaxy takes over. For decades, scientists at NASA and institutions like Caltech modeled this boundary using physics and indirect observation. They predicted a layered structure. First, the termination shock, where the solar wind slows abruptly. Then the heliosheath, a turbulent region where solar and interstellar particles mix. And finally, the heliopause, the outermost edge, a kind of frontier, a place where the influence of our sun effectively ends. Voyager 1 was heading straight toward it, and as it approached, its instruments began to detect changes that matched these models. The solar wind slowed down, particle densities shifted, cosmic ray intensity increased. Everything pointed to an imminent crossing, but when the moment finally came, it did not look like a crossing at all. There was no sharp boundary, no clear transition. Instead, the data suggested something far more complex. According to NASA, one of the most important indicators of crossing the heliopause was the sudden increase in galactic cosmic rays. These high-energy particles originating from distant stars and supernova explosions are usually deflected by the heliosphere. Inside the bubble, their intensity is lower. Outside, it rises dramatically. Voyager 1 detected exactly that. At the same time, the solar wind dropped to nearly zero. This combination of signals strongly indicated that the spacecraft had entered interstellar space, and yet something did not match: the magnetic field. Scientists expected a noticeable shift in the direction of the magnetic field lines, reflecting the transition from the sun's influence to the galaxy's broader magnetic structure. But Voyager 1 did not detect a dramatic change. Instead, the magnetic field direction remained surprisingly consistent. This was unexpected, and it introduced the first real complication, because if the magnetic field did not change as predicted, then perhaps the boundary was not as simple as the model suggested. Perhaps it was not a clean separation at all. Instead, it might be a region of interaction, a place where solar and interstellar influences blend, overlap, and create structures we had never directly observed. This idea was supported by further analysis. A study published in Science suggested that the heliopause might be more like a porous boundary than a solid one. Rather than a sharp edge, it could allow particles and magnetic fields to leak across, creating a complex dynamic interface. In other words, Voyager 1 was not simply crossing a line. It was entering a transition zone, a region where the rules change gradually and where multiple influences coexist. This has profound implications, because if the boundary is not clean, then the environment beyond it may not be uniform. It may contain variations, fluctuation, localized structures that behave differently from one region to another. And this is where the mystery begins to connect with the signal, because Voyager 1's strange transmission did not start immediately after crossing the heliopause. It appeared later, deeper into interstellar space, which suggests that whatever is affecting the spacecraft may not be the boundary itself, but something beyond it, something within the interstellar medium. This raises an important question. What exactly is interstellar space? It is easy to imagine it as empty, a vast void with nothing in it. But that is not entirely accurate. Interstellar space is filled with plasma, a state of matter where atoms are ionized into charged particles. This plasma is extremely thin, far less dense than anything we experience on Earth, but it's not uniform. It contains waves, magnetic fields, regions of varying density and temperature. And according to data from Voyager 1, it may also contain structures that we do not fully understand. One of the key discoveries made by Voyager 1 after crossing the heliopause was the detection of plasma oscillations. These are waves in the density of charged particles similar in concept to sound waves in air. By measuring these oscillations, scientists were able to estimate the density of the interstellar medium. And what they found was surprising. The density was higher than expected. Not dramatically higher, but enough to suggest that interstellar space is more complex than the simplified models had predicted. This complexity matters because plasma and magnetic fields can interact with electromagnetic signals. They can influence how radio waves propagate. They can introduce subtle distortion, and under certain conditions they can even alter the way information is encoded or interpreted, at least in theory. Before Voyager 1, this was largely speculative. There was no direct evidence that such effects could impact a spacecraft's telemetry in a meaningful way. But now, with the strange transmission being received, that possibility can no longer be ignored, because the timing is too significant. Voyager 1 enters interstellar space. It begins detecting unexpected plasma conditions, and sometime later its data starts behaving in ways that do not match any known internal failure. This does not prove that the environment is responsible, but it suggests a connection, a link between the space Voyager 1 is travelling through and the signal it is sending back. And that link is what scientists are now trying to understand. Because if interstellar space can influence a spacecraft's communication systems even subtly, then Voyager 1 is not just exploring that environment. It is interacting with it in ways we're only beginning to notice. And that brings us to the moment when the mystery truly revealed itself. Because up to this point, everything could still be explained as complexity, as refinement, as unexpected but understandable behavior. But then, something happened that no one had predicted. Something that turned a subtle anomaly into a full-scale puzzle. The signal changed. And when it did, it forced scientists to confront a possibility they had not seriously considered before. That the problem might not be just complicated. It might be something entirely new. It did not arrive as silence. It did not arrive as chaos. It arrived as something far more unsettling. A signal that looked correct, and yet contained information that should not exist. Sometime after Voyager 1 had already crossed into interstellar space, engineers monitoring its telemetry noticed a shift that could not be ignored anymore. The spacecraft was still transmitting. The signal strength was steel. The carrier wave, the underlying radio transmission, was clean and precisely locked onto Earth. But the data inside that signal had changed. According to NASA updates, the telemetry from Voyager 1's attitude, articulation and control system began returning values that were impossible. Not just slightly wrong, impossible. Numbers that did not correspond to any physical states the spacecraft could be in. Values that exceeded expected ranges. Readings that suggested conditions that simply did not exist. And yet the spacecraft itself showed no signs of distress. Its antenna remained perfectly aligned. Its power systems were stable. Its communication link was intact. Everything about its behaviour suggested that it was functioning normally, except for the data it was reporting. This is what made the situation so alarming, because in space exploration, telemetry is the only way we understand what a spacecraft is doing. There are no cameras watching Voyager 1 from the outside, no way to physically inspect its systems. Everything we know comes from the numbers it sends back, and now those numbers could not be trusted. Imagine trying to diagnose a machine when every sensor is lying to you. Not randomly, not erratically, but consistently in a way that appears structured but does not reflect reality. That is what engineers were facing. At first they attempted the simplest explanation. Memory corruption. Voyager 1's onboard systems rely on extremely old hardware, including memory that has been exposed to radiation for decades. A single corrupted memory location could potentially alter how data is processed or transmitted. So engineers began analysing the telemetry for signs of bit errors. They looked for patterns that would indicate random flips. They compared current data to historical baselines. But what they found did not match the profile of typical memory corruption. The errors were too organised, too consistent, too stable for a time. Instead of random glitches, the data appeared to follow a pattern, as if the system generating the telemetry was operating under a different set of rules. This led to a more specific hypothesis. What if the issue was not random corruption, but a fault in the flight data subsystem? This subsystem is responsible for collecting information from various parts of the spacecraft and formatting it into a coherent stream of telemetry. If something in this system were malfunctioning, it could potentially produce incorrect data, while the rest of the spacecraft continued to function normally. So engineers focused their attention there. They began sending diagnostic commands designed to probe the subsystem's behavior. They attempted to isolate which parts of the data stream were affected. They tried to identify whether the problem was localized or systemic. And once again, the results were unexpected. Because the subsystem appeared to be functioning, it responded to commands. It processed inputs. It continued to transmit data in the correct format. There were no signs of total failure, only incorrect output. At this point, the situation had escalated beyond a routine anomaly. It had become a mystery, because every known explanation left something unresolved. If it were a hardware failure, why was the signal still perfect? If it were a software issue, why did the system continue to behave consistently? If it were radiation damage, why were the errors not random? Each answer raised new questions, and none of them fully explained what was happening. This is what scientists sometimes refer to as a clean anomaly. An event that clearly deviates from expectations but does so in a way that is structured, repeatable, and persistent. These are the most difficult problems to solve, because they do not point to obvious causes. They require deeper investigation, new ideas, sometimes even new physics. But before jumping to extraordinary conclusions, engineers needed to exhaust every conventional possibility. They began testing alternative communication pathways within the spacecraft. Voyager 1 has redundant systems designed to provide backup options in case of failure. By rerouting data through different pathways, engineers hoped to determine whether the problem was confined to a specific component. This process was slow. Every command sent to Voyager 1 takes more than 20 hours to arrive. Every response takes just as long to return. A single test cycle can take nearly 2 days, and yet the team continued, patiently, carefully, methodically. And over time a clearer picture began to form. The issue appeared to be associated with how the flight data subsystem was accessing memory. Not a complete failure, not a total loss of function, but something more subtle, as if the system was reading from the wrong location, or interpreting incorrect. This could explain why the telemetry was structured but incorrect. The system was still following its programming, but it was working with corrupted or misplaced information. However, even this explanation was incomplete, because it did not fully account for the stability of the error. Memory issues typically evolve over time. They worsen, they spread, but Voyager 1's anomaly remained remarkably consistent. It did not degrade further. It did not collapse into chaos. It stayed stable. And that stability suggested something else might be at play, something that was maintaining the error, preserving it, as if the system had settled into a new state, a state that was not part of its original design. This is where the mystery deepens even further, because a stable incorrect state is harder to explain than a failing one. It implies equilibrium, balance, a system that has adapted in some way to new conditions, and those conditions may not be entirely internal. Because Voyager 1 is no longer operating in the environment it was built for. It is moving through interstellar space, a region filled with plasma magnetic fields and phenomena that we are only beginning to understand. And while there is no direct evidence that this environment is causing the anomaly, there is also no way to rule it out completely, because we have never tested a spacecraft under these conditions before. Voyager 1 is the test, and its strange transmission may be the result. A result that challenges our assumption. That forces us to reconsider what we thought we knew, and that leaves us with a question that is both simple and unsettling. If the spacecraft is still functioning, and the signal is still perfect, then what exactly has changed? At this point, the situation stopped being a technical problem, and became something far more uncomfortable. Because every explanation that should have worked didn't. The engineers working with Voyager 1 were not dealing with a silent spacecraft or a broken one. They were dealing with a system that behaved correctly in every observable way, except in the one place that mattered most, its data. And that contradiction created a kind of tension, a growing uncertainty that could not be resolved through normal troubleshooting. Inside mission control teams began revisiting every assumption they had made. They rechecked calibration models. They compared Voyager 1's data with historical records stretching back decades. They even reanalyzed how ground-based systems were interpreting the signal just to rule out the possibility that the error was on Earth. But the results were consistent. The signal arriving at the Deep Space Network was clean, accurate in structure, stable in strength, and yet when decoded, it produced values that did not correspond to reality. This ruled out one of the most comforting possibilities, that the problem was on our side. It wasn't, which meant the mystery remained out there, billions of kilometers away. This is where the confusion deepened, because engineers began to notice something even stranger. Not all data from Voyager 1 was affected. Some systems continued to report normal values, others did not. This selective inconsistency made the problem harder to isolate. If the entire data stream were corrupted, it would suggest a broad system failure. If only one sensor were affected, it would point to a localized issue. But Voyager 1 was somewhere in between, partially correct, partially incorrect, and that blurred line made diagnosis extremely difficult. According to NASA engineers, the spacecraft's communication subsystem was functioning normally. Commands were received and executed. Responses were transmitted back on schedule. This meant that the core communication link, the most critical system, was intact, which raised an unsettling possibility. The spacecraft was still listening, still responding, still operating with a kind of internal logic, but that logic was producing outputs that no longer matched reality. To understand why this is so strange, imagine a calculator that always gives answers. It responds instantly, it follows its programming, but the answers are subtly wrong, not random, not obviously broken, just incorrect in ways that are hard to trace. That is the kind of behavior Voyager 1 was exhibiting, and it forced scientists to confront something they rarely have to consider: the possibility that the system is working, but no longer behaving as expected. This is not the same as failure. It is something more ambiguous, a shift, a deviation, a state where cause and effect are no longer clearly aligned. As the investigation continued, engineers began to map out which parts of the spacecraft were still reliable. They identified subsystems that continued to produce consistent, believable data. They compared those against systems that showed anomalies, and gradually a pattern began to emerge. The issue appeared to be concentrated around the flight data subsystem, specifically how it was processing and formatting telemetry before transmission. This aligned with earlier Shakespeare hypotheses, but it did not fully explain why the problem had appeared in the first place, or why it remained stable, or why it affected some data and not others. This is where the confusion turned into something more profound, because the more scientists tried to isolate the issue, the more it seemed to resist simple classification. It was not purely hardware, not purely software, not purely environmental. It was something in between. And that in-between space is where science becomes most uncertain, because it is where existing models begin to break down, where categories blur, where explanations that once seemed sufficient no longer hold. At this stage, discussions among scientists began to expand beyond engineering. Physicists were brought in, experts in plasma behavior, researchers who study how electromagnetic signals interact with charged particles in space. Because one possibility, however unlikely, could not be ignored. What if the signal itself was being altered after it left the spacecraft? Not destroyed, not weakened, but modified, subtly, in ways that preserved its structure while changing its content. This idea challenges one of the fundamental assumptions of deep space communication, that radio waves travel through space largely unaffected, except for predictable delays and minor distortions. But interstellar space is not completely empty. It contains plasma, magnetic fields, waves of charged particles that can interact with the electromagnetic radiation. Under certain conditions, these interactions can produce effects that are not fully understood. Effects that may alter the phase or encoding of a signal without significantly reducing its strength. This is not a confirmed explanation. It is a possibility, a hypothesis, but it is one that becomes more relevant when internal explanations fall short. Because Voyager 1 is no longer operating within the well-characterized environment of the heliosphere, it is in a region where direct measurements are rare, where models are based on limited data, where new phenomena may exist, And if such phenomena can influence how signals propagate, then the anomaly may not be entirely within the spacecraft. It may be partly within the space between the spacecraft and Earth. This idea introduces a new layer of complexity, because it means that the data we receive may not be a perfect representation of what Voyager 1 is sending. It may be transformed, not randomly, not chaotically, but systematically, in a way that we do not yet fully understand. And that possibility is both fascinating and deeply unnerving, because it suggests that even when we think we are receiving clear information from deep space, we may still be missing something hidden in the transmission itself. As scientists continue to explore these possibilities, they realize that they were no longer just trying to fix a spacecraft, they were trying to understand a phenomenon that sits at the intersection of engineering, physics, and the unknown behavior of interstellar space. And that realization marked a turning point, because it meant that the mystery was no longer just about Voyager 1. It was about the nature of space itself. And to solve it, scientists would need to consider not just one explanation, but many, some conventional, some speculative, all incomplete, because at this stage no single theory could account for everything. And that's exactly where the story becomes even more complex. Because when one explanation is not enough, science begins to branch into competing ideas, competing models, competing visions of what might be happening out there beyond the edge of our solar system. When a mystery refuses to resolve itself, science does not stop. It multiplies. Different explanations begin to emerge, each one trying to account for the same set of facts, each one explaining part of the puzzle, but not all of it. And that's exactly what began to happen with Voyager 1. There was no single answer. Instead, there were competing theories, some grounded firmly in engineering, others reaching into the less understood behavior of interstellar space. All of them shaped by the same constraint. The signal is stable, stable. The data is not. The first and most conservative explanation remained an onboard fault. Engineers at NASA focused on the possibility that the flight data subsystem had encountered a memory issue. Voyager 1 uses extremely limited onboard memory by modern standards. Its systems rely on fixed memory locations to store instructions and data. If a small section of that memory were corrupted, it could cause the system to read from the wrong addresses. This would not necessarily stop the spacecraft from functioning, but it could cause it to report incorrect values. In this scenario, the spacecraft is still operating correctly. It is still pointing its antenna, still receiving commands, still executing instructions. But when it tries to describe its state, it is pulling information from the wrong place. This would explain the structured nature of the error, the consistency, the stability, because the system is not failing. It is simply misaligned. This theory has strong support. It fits many of the observed symptoms, but it does not explain everything. It does not fully account for why the issue appeared when it did, or why it has remained so stable over time. And that leaves room for other ideas. The second theory moves beyond the spacecraft itself. It focuses on the environment, specifically the interstellar medium. According to research published in journals like Astrophysical Journal Interstellar Space, is not uniform. It contains variations in plasma density, magnetic turbulence, and wave-like structures that can interact with electromagnetic signals. These interactions are usually subtle. They might cause slight delays, minor distortions, but under certain conditions they could produce more complex effects. Some scientists have proposed that Voyager 1 may be travelling through a region of plasma with unusual properties, a region where charged particles and magnetic fields interact in ways that influence how radio waves propagate. In this scenario, the spacecraft is sending correct data, but the signal is being altered as it travels through space. Not enough to weaken it, but enough to change how the data is interpreted on Earth. This could produce a signal that appears clean, but contains distorted information. It is a compelling idea, because it explains the contradiction between signal quality and data integrity. But it also raises new questions. If the signal is being altered, why only certain parts of the data? Why does some telemetry remain correct while other parts do not? And why has this effect not been observed more clearly in other deep space missions? To explore that, scientists turn to a comparison. Voyager 2. Voyager 2 followed a different trajectory. It crossed the heliopause in 2018 years after Voyager 1, and it entered interstellar space at a different location. By comparing data from both, spacecraft scientists hope to identify whether the anomaly was unique to Voyager 1 or part of a broader phenomenon. So far, Voyager 2 has not shown the same type of data inconsistency. Its telemetry has remained largely consistent with expectations. This suggests that the issue may not be a universal feature of interstellar space. Instead, it may be localized, something specific to the region Voyager 1 is traveling through. And that brings us to a third theory, one that combines elements of both internal and external explanations, a hybrid model. In this view, the spacecraft may have experienced a small internal fault, perhaps a memory issue, perhaps a degradation in a specific component. But that fault alone does not fully explain the observed behavior. Instead, it interacts with the external environment. The interstellar medium amplifies or stabilizes the anomaly. In other words, the spacecraft and its environment are working together to produce the effect. This is a more complex explanation, but it may also be more realistic, because real-world systems rarely operate in isolation. They are influenced by their surroundings, especially in environments that are not fully understood, and interstellar space is exactly that. A frontier, a place where our models are still evolving, where direct measurements are rare, where new discoveries are still being made. For example, Voyager 1 has detected plasma waves that were stronger and more structured than expected. These waves, caused by disturbances in the interstellar medium, provide valuable information about particle density and magnetic field interactions. But they also hint at a level of complexity that was not fully anticipated, a complexity that could in theory influence how signal boosters behave, even if only slightly. And when you combine that with an aging spacecraft operating with decades-old technology, the result may be something we have never seen before. A system that is partially affected by internal limitations and partially influenced by external conditions. A system that produces data that is neither completely wrong nor completely right. And that is what makes this mystery so difficult to resolve. Because each theory explains part of the picture, but none of them explain all of it. The onboard fault theory explains the structured error. The environmental theory explains the possibility of signal distortion. The hybrid theory explains the interaction between the two. But there are still gaps, still unanswered questions. And in science, those gaps are where new discoveries are often hiding, because sometimes the truth is not found in choosing one explanation over another. It is found in understanding how multiple factors combine, how systems interact, how unexpected behaviors emerge from complex conditions, and that's exactly what scientists are trying to do now. They're not just looking for a single cause, they're exploring a range of possibilities, testing hypotheses, comparing data, refining models, all while Voyager 1 continues to drift farther away, carrying its mystery with it, sending back signals that are both familiar and strange, signals that may contain answers, if only we can learn how to interpret them. And that leads to the next stage of this story. Because as scientists debated these competing theories, new data began to emerge. Data that would bring them closer to understanding what was really happening. Not a complete answer, but a breakthrough. A way to begin connecting the pieces. And for the first time, a glimpse of how this puzzle might eventually be solved. Breakthroughs in science rarely arrive as dramatic moments. They emerge slowly, piece by piece. From persistence, patience, and the willingness to question every assumption. And that's exactly how the first real progress in the Voyager mystery began. After months of analysis, engineers working with Voyager 1 started focusing on a very specific possibility. Not a total system failure, not an environmental distortion, but something far more precise, a problem in memory addressing. According to NASA engineers at the Jet Propulsion Laboratory, Voyager 1's flight data subsystem relies on fixed memory locations to store and retrieve information. Each piece of telemetry, every value describing the spacecraft's state is pulled from a specific address. If those addresses are accessed incorrectly, the system might still function, but it would retrieve the wrong data. And that is exactly what the new analysis suggested. Engineers began to suspect that a small section of Voyager 1's memory had become corrupted, not completely destroyed, but damaged enough to disrupt how data was being read. Instead of accessing the correct memory locations, the subsystem was pulling information from unintended areas. This would explain the structured nature of the anomaly, the consistency, the stability, because the system was not failing. It was simply reading the wrong information in a consistent way. To test this theory, engineers devised a series of carefully planned commands. Each command was designed to probe different parts of the spacecraft's memory, to see how it responded, to determine whether the issue could be isolated. This process was slow. Every command took more than 20 hours to reach Voyager 1. Every response took just as long to return. A single test cycle required nearly 2 days. But over time, the data began to reveal something important. The anomaly was not random. It was localized, confined to a specific region of memory. This was a crucial insight, because it meant the rest of the system was still intact, still reliable, still capable of functioning correctly, and that opened the door to a possible solution. If the corrupted memory region could be identified, it might be possible to bypass it, to reroute the data processing, to instruct the spacecraft to use a different section of memory instead. In other words, to work around the problem. This is not something Voyager 1 was originally designed to do. Its systems are simple by modern standards. They do not have the flexibility of contemporary software, but they do have some level of redundancy, some ability to adapt, and that is what engineers began to They crafted new commands, instructions that would change how the flight data subsystem accessed memory. They attempted to redirect operations away from the suspected faulty region. It was a delicate process. One mistake could disrupt communication entirely, and there would be no way to physically repair the spacecraft. Everything had to be done remotely, carefully, step by step, and then they waited for nearly 2 days, as the command traveled across billions of kilometers of space, until finally the response arrived. And when it did, something had changed. The data. It was different. Not completely normal, not fully restored, but improved. Some of the previously corrupted values began to make sense again. Certain telemetry fields returned to expected ranges. The spacecraft was still not fully understood, but it was no longer entirely incomprehensible. This was the first real breakthrough, a confirmation that the anomaly was at least in part internal, a problem with how the spacecraft was handling its own data. But even this breakthrough did not solve everything, because while some data improved, other parts remained inconsistent. The anomaly had been reduced, but not eliminated, which suggests something important. The memory issue may be part of the problem, but it may not be the entire problem. And this is where the story becomes even more interesting, because the partial success of the fix introduces a new possibility. That multiple factors are at play, an internal fault, combined with external conditions, working together to produce the observed behavior. This idea aligns with earlier hybrid theories, but now it has evidence, because if the problem were purely internal, the fix should have resolved it completely, and if it were purely external, the fix should have had no effect. The fact that it had a partial effect suggests an interaction, a system influenced by both its internal state and its environment. And that brings us back to interstellar space, because Voyager 1 is not operating in isolation. It's immersed in a medium that we are only beginning to understand, a medium filled with plasma magnetic fields and subtle variations that can influence how signals behave. And while the memory issue explains part of the anomaly, it does not fully explain why the remaining inconsistencies persist, why certain data still does not align with expectations, why the signal continues to carry traces of something unexplained. This is where scientists begin to shift their perspective, from solving a problem to understanding a phenomenon, because Voyager 1 is not just a spacecraft, it is a probe, a sensor, a messenger from a region of space we have never directly explored before. And the data it sends back, even when imperfect, may contain information about that region, information hidden within the anomalies, within the inconsistencies, within the parts that do not quite make sense. And that is what makes this breakthrough so important. It does not end the mystery. It transforms it from a question of failure into a question of discovery, because now scientists know that part of the problem can be explained, but not all of it. And the part that remains unexplained may be the most important part, because it may be telling us something about interstellar space itself. Something we did not expect, something we did not predict, something that Voyager 1 has encountered and is now trying to show us, even if we do not yet fully understand how to read it. And that leads to the next step in this journey. Because once you begin to understand part of a mystery, you can start to ask a deeper question. Not just what is happening, but why? To understand what might be happening to Voyager 1, it helps to step away from the equations, the telemetry, the complexity of space physics, and imagine something much simpler. Imagine you are sending a message across a vast distance. You write it clearly. You structure it carefully. Every word is in the right place. Then you hand it to someone who must carry it across a long and unfamiliar landscape. A landscape filled with fog-shifting terrain and invisible currents. When the message finally arrives, it is still readable. The sentences are intact, but some of the words have changed. Not randomly, not destroyed, just altered in ways that make the meaning harder to understand. That is what Voyager 1's transmission may represent. A message that is being shaped, not broken, modified, not erased. Because the key to this mystery lies in one. The signal itself is still perfect. According to NASA, the carrier wave remains stable. The spacecraft is still locked onto Earth. The communication link is intact, which means the message is getting through. But something about the content of that message is being changed. And to understand how that could happen, we need to look at the medium the signal is travelling through. Interstellar space. It's often described as empty, but in reality it is more like an extremely thin ocean, not of water but of plasma. Charged particles, magnetic fields, subtle waves that move through this medium in ways that are not always intuitive. In plasma physics, waves can carry energy and information. They can interact with electromagnetic signals, and under certain conditions they can influence how those signals behave. For example, when radio waves travel through plasma, they can experience dispersion. Different frequencies travel at slightly different speeds. This can stretch or compress parts of the signal. Usually this effect is small, predictable, correctable, but Voyager 1 is not operating in a typical environment. It's billions of kilometers from the Sun, far beyond the regions we've studied in detail, and the plasma it is moving through may have properties we do not fully understand. According to studies published in journals like Nature, interstellar plasma can form structures, regions of varying density, magnetic fluctuations, wave patterns that can propagate over large distances. If Voyager 1 is moving through one of these regions, its signal could be interacting with it in subtle ways, not enough to disrupt the signal completely, but enough to influence how the data is encoded or interpreted. Now combine that with what we already know. Voyager 1 has a partially corrupted memory region. Its flight data subsystem is not functioning perfectly. It's already producing data that may not be entirely accurate, and that data is then transmitted through an environment that may further influence the signal. This creates a layered effect. The spacecraft generates imperfect data. The interstellar medium subtly alters the signal, and by the time it reaches Earth, what we receive is a combination of both. Still structured, still coherent, but not entirely faithful to the original state. This layered explanation does not require exotic physics. It does not require unknown forces. It simply requires two known factors interacting in a way we have not previously observed: an aging spacecraft and a complex environment. Together they produce a result that neither would create alone. And that is often how new phenomena emerge, not from entirely new elements, but from new combinations of familiar ones. This is why the Voyager anomaly is so valuable, because it forces us to think about systems as interconnected, not isolated. The spacecraft is not just a machine, it's part of its environment, and its behavior reflects that interaction. To make this even clearer, imagine shining a flashlight through clear air. The beam travels straight, unchanged. Now imagine shining that same flashlight through a dense fog. The light still reaches the other side, but it is scattered, diffused, altered, not destroyed, just changed. Voyager 1's signal may be experiencing something similar, except instead of visible light and fog, we are dealing with radio waves and plasma, and instead of simple scattering, we are dealing with subtle shifts in how information is encoded. This does not mean the signal is unreliable. It means it is more complex than we assumed. And complexity is where new understanding begins. Because if interstellar space can influence signals in this way even slightly, it opens up new possibilities. It suggests that the space between stars is not just a passive backdrop. It is an active medium, a medium that can shape the information passing through it. And that has implications far beyond Voyager 1. It affects how we interpret signals from distant spacecraft, how we analyze radio emissions from other stars, even how we search for signals that might originate from beyond our solar system. Because if the medium can alter the message, then understanding the medium becomes just as important as understanding the source. And that's exactly what Voyager 1 is helping us do. Not intentionally, not by design, but through the unexpected behavior of its own transmission. It is revealing the complexity of interstellar space, one anomaly at a time. And while we may not yet have a complete explanation, we now have something just as important: a framework, a way of thinking about the problem that connects the spacecraft to the signal and the environment. And that framework allows scientists to move forward, to test new ideas, to refine their models, to explore the deeper implications of what Voyager 1 is showing us. Because once you understand how something might be happening, the next question becomes inevitable. If this is happening here, could it be happening elsewhere? If the strange transmission from Voyager 1 is not just a localized glitch, if it reflects something deeper about how signals behave in interstellar space, then its implications stretch far beyond a single spacecraft. Because Voyager 1 is not alone in the universe. It is simply the first object to travel through this region, the first to send back continuous data from beyond the heliosphere. And what it reveals may apply everywhere. To understand why, consider how we study the universe. Much of modern astronomy relies on signals, light, radio waves, X-rays, gamma rays. All of these are forms of electromagnetic radiation traveling across vast distances, carrying information from distant stars, galaxies, and cosmic events. We interpret these signals to understand what is happening in places we cannot directly observe. We assume that what we receive accurately represents what was sent, but Voyager 1 introduces a subtle challenge to that assumption. Because if the medium between the source and the observer can alter the signal even slightly, then our interpretations may need to account for those effects. This is not a new idea. Astronomers already consider factors like redshift, where the expansion of the universe stretches the wavelength of light, shifting it toward the red end of the spectrum. They account for interstellar dust, which can absorb and scatter light-dimming distant objects. They correct for gravitational lensing, where massive objects bend the path of light. But the Voyager anomaly suggests something more nuanced. Not just a change in intensity or wavelength, but a potential influence on the structure of the signal itself. And if that is true, it could have implications for how we interpret data from across the galaxy. For example, radio astronomers often study signals that pass through interstellar plasma. These signals can experience dispersion, where different frequencies arrive at slightly different times. This effect is well understood and used to estimate distances to pulsars and other objects. But what if there are additional effects, subtle interactions that do not just delay signals but modify their internal structure? These effects might be small, difficult to detect, but over vast distances even small changes can accumulate. And that means the signals we receive from distant sources might carry signatures not just of their origin, but of the space they travelled through. Voyager 1 provides a unique opportunity to study this. Because unlike distant astronomical sources, we know exactly what Voyager 1 is supposed to be sending. We know its systems, its encoding methods, its expected telemetry. This allows scientists to compare what is sent with what is received, and that comparison can reveal the influence of the medium in ways that are difficult to detect with other sources. In a sense, Voyager 1 is acting as a calibration tool, a known signal passing through an unknown environment, and the differences between expectation and observation may contain valuable information. Information about the structure of interstellar space, about plasma behavior, about magnetic field interactions, and possibly about phenomena we have not yet fully described. This idea extends even further when we consider other star systems. Every star has its own version of a heliosphere, a bubble created by stellar winds interacting with the surrounding interstellar medium. The boundaries of these bubbles may vary. Some may be larger, some smaller, some more turbulent. If Voyager 1's experience is influenced by the structure of our heliosphere and the surrounding interstellar medium, then similar effects could occur around other stars. This means that the signals we detect from distant systems may also be shaped by their local environments, not just by the source itself. And that adds a new layer of complexity to our understanding of the universe, because it suggests that space is not just a passive backdrop. It is an active participant, a medium that can influence, modify, and shape the information passing through it. This idea is supported by observations from other missions and instruments. For example, data from the Hubble Space Telescope and the James Webb Space Telescope have revealed complex structures in interstellar space, including filaments of gas regions of varying density and interactions between stellar winds and the surrounding medium. These structures are not uniform, they are dynamic, they evolve over time, and they can influence how light and other signals propagate. Voyager 1 is moving through one of these regions, a specific location in the galaxy with its own unique properties, and its anomalous transmission may be a reflection of that environment, a signature of the space it is travelling through. If that is the case, then the anomaly is not just a problem to be solved, it is a source of information. A clue, a way to study interstellar space from within, and that changes how we think about it. Because instead of asking what is wrong with Voyager 1, we begin to ask what is Voyager 1 showing us? What is it revealing about the space between stars? What patterns are hidden within its transmission? What can we learn from the differences between expectation and reality? These questions are not easy to answer. They require new models, new approaches, new ways of interpreting data, but they also open the door to new discoveries. Because every time we encounter something that does not fit our current understanding, it forces us to expand that understanding, to refine it, to improve it. And that is how science moves forward. Voyager 1 in its quiet, persistent way is doing exactly that. It is challenging assumption. It is revealing complexity. It is pushing the boundaries of what we know, and it is doing so from a place we have never explored before, far beyond the influence of our scene. Deep within the vast, largely unknown environment of interstellar space. And as we continue to study its transmission, one thing becomes increasingly clear. The anomaly is not just about Voyager 1. It is about the nature of the universe itself. And that leads to an even more profound realization. Because if our understanding of interstellar space is incomplete, then what else might we have misunderstood about the cosmos? When a single anomaly begins to reshape how we think about space, its consequences do not stay contained. They spread, quietly at first, then more visibly as new models, new interpretations and new questions begin to ripple outward through the scientific community. And that is exactly what has happened with Voyager 1, because this is no longer just about one spacecraft sending confusing data. It is about what that data implies, about how it challenges assumptions that have guided space science for decades, and about how it forces us to rethink the nature of the space between stars. For a long time, interstellar space was treated as a relatively simple environment. Sparse, predictable, largely uniform, a backdrop against which the real drama of the universe, stars, planets, galaxies would unfold. But Voyager 1 suggests something different, something more dynamic, more structured, more interactive. According to NASA and collaborating researchers, the spacecraft's measurements of plasma density, magnetic field fluctuations, and particle behavior indicate that interstellar space may be far more complex than previously believed. Not chaotic, but layered, filled with subtle variations that can influence physical processes in ways we are only beginning to understand. And if that is true, then the implications are significant. Because it means that every signal travelling through space is travelling through a medium that matters, a medium that can shape what we receive. This affects not only spacecraft like Voyager 1, it affects how we interpret signals from distant astrophysical sources, radio emissions from pulsars, light from distant galaxies, even the faint background radiation left over from the early universe. All of these signals pass through interstellar and intergalactic media. And if those media are more complex than we assumed, then our interpretations may need to account for that complexity. This does not mean that our current understanding is wrong, but it may be incomplete, and incompleteness is where refinement begins. For example, consider the study of fast radio bursts, brief intense flashes of radio waves originating from distant galaxies. These signals travel across billions of light years before reaching Earth. Scientists analyzed their dispersion the way different frequencies arrive at slightly different times to learn about the medium they pass through. But if there are additional effects, subtle distortion, structural modifications, then those signals may contain more information than we currently extract. Or in some cases, they may be slightly misinterpreted. Voyager 1 provides a closer, more controlled example of this process. A known source, a known signal, passing through a region we are still trying to understand, and the discrepancies we observe may be the first direct evidence of how that medium can influence communication. This has practical implications as well. Future deep space missions will travel even farther than Voyager 1. They will rely on communication systems that must operate across vast distances. If interstellar space can influence signals even slightly, engineers will need to design systems that can account for those effects. More robust encoding, better error correction, more adaptive communication strategies, because what works within the heliosphere may not work the same way beyond it, and as humanity continues to explore that boundary will become increasingly important. Voyager 1 is the first to cross it, but it will not be the last. Missions like the proposed interstellar probes concepts studied by organizations such as ESA and NASA aim to travel even deeper into interstellar space, carrying more advanced instruments and communication systems. These missions will build on what Voyager 1 has revealed. They will test new models, they will explore new regions, and they will help us understand whether the anomaly observed in Voyager 1 is unique or part of a broader pattern. Because if similar effects are observed elsewhere, it would confirm that interstellar space is not just complex, but consistently influential. A medium that must be understood, not ignored, and that realization extends beyond engineering and astronomy. It touches something more fundamental, our perception of the universe. For centuries we have imagined space as empty, a vast void separating objects, but in reality space is filled with structure, with fields, with particles, with interactions that shape the behavior of matter and energy. Voyager 1 is reminding us of that, in a subtle way, through a signal that does not quite behave as expected, through data that challenges our assumptions, through a mystery that forces us to look deeper. Because sometimes the most important discoveries are not the ones that confirm what we know, they are the ones that reveal what we do not know. And that is what Voyager 1 is doing now. It is not just sending data, it is revealing the limits of our understanding, and in doing so it is expanding those limits, pushing them outward, into the unknown, where new questions wait, where new discoveries are possible, and where the universe becomes just a little more complex and a little more fascinating than we thought. And yet even with all of these implications, one thing remains clear. We still do not have a complete answer. We understand more than we did before, but not everything, because there are still aspects of this anomaly that do not fit any current model, still questions that remain unresolved. And those questions lead us to the next stage of this story, the part where science confronts its own limits and asks what do we still not understand even after the breakthrough, even after the partial fix, even after months of analysis and debate. There are still questions that no one can answer. And that is what makes the signal from Voyager 1 so compelling, because in science, solving part of a mystery often reveals how much of it remains unsolved. We now understand that part of the anomaly likely comes from a memory issue within the spacecraft, a damaged region causing data to be misread. We also understand that interstellar space is more complex than we once believed, that it contains plasma structures and magnetic variations that may influence how signals travel. But these explanations even combined do not fully account for everything we are observing. There are still gaps, still inconsistencies, still aspects of the signal that do not fit neatly into any current model, and those gaps point to the limits of our knowledge. Because Voyager 1 is operating in a region of space that we have never directly explored before, a region where our understanding is based on theory, indirect observation, and a single spacecraft. That is not a lot of data, not enough to build a complete picture. According to researchers working with NASA, one of the biggest challenges is that we cannot verify Voyager 1's environment directly. We cannot send another probe to the exact same location. We cannot observe the same conditions from multiple angles. We have only one perspective, one stream of data, and that makes interpretation difficult, because when something unexpected appears in that data, it is hard to determine whether it represents a universal phenomenon or a localized event. Is Voyager 1 passing through a unique region of interstellar space? A pocket of plasma with unusual properties? A magnetic structure that exists only in that specific location? Or is it revealing something more general? Something that applies across the galaxy? At this point we do not know, and that uncertainty is important, because it reminds us that our models of interstellar space are still incomplete. They are based on limited observations, on assumptions that have not been fully tested. Voyager 1 is beginning to test them, but it is only one data point. Another unanswered question lies in the nature of the signal itself. Why does the anomaly affect some telemetry and not others? Why do certain values return to normal after adjustments while others remain inconsistent? If the problem were purely internal, we would expect a more uniform pattern. If it were purely external, we might expect a broader effect on the signal. Instead, we see something selective, something that affects specific parts of the data stream, and that selectivity is difficult to explain. It suggests that the interaction between the spacecraft and its environment is not uniform, that certain types of data, certain frequencies, or certain encoding methods may be more sensitive to these effects than others. But this is still a hypothesis. We do not yet have enough evidence to confirm it. There is also the question of time. Why did the anomaly appear when it did? Voyager 1 has been in interstellar space for years. Why did the signal remain consistent for so long and then begin to show these issues? Was it a gradual process that only became noticeable recently? Was it triggered by a specific event, a change in the spacecraft, a change in the environment, or a combination of both? Again, we do not know. And perhaps the most fundamental question of all is this. What exactly is the interstellar medium at the scale Voyager 1 is experiencing? We have models, we have indirect measurements, we have theoretical frameworks, but we do not have a complete detailed map of the structures that exist out there. We do not fully understand how plasma behaves at these scales, how magnetic fields interact over such vast distances, how waves propagate through this environment. And without that understanding, it is difficult to fully interpret what Voyager 1 is showing us. This is the nature of exploration. Every new frontier reveals both answers and questions, and often the questions are more important because they guide future research. They point to areas where our understanding needs to improve. They highlight the limits of what we know. Voyager 1 is now operating at those limits, at the edge of our knowledge, and its strange transmission is a reminder of that. A signal that says, in effect, we do not yet understand everything. Not about the spacecraft. Not about the space it is travelling through. Not about the interaction between the two. And that is not a failure. It is an opportunity to learn, to refine our models, to develop new theories, to design new experiments, because every unanswered question is a starting point, a place from which discovery begins. And Voyager 1 in its quiet distant journey is providing many such starting points. Each anomaly, each inconsistency, each unexplained detail, a clue, a hint, a piece of a larger puzzle. A puzzle that extends far beyond a single spacecraft, into the nature of interstellar space, into the behavior of matter and energy at the larger scales, into the fundamental workings of the universe. And while we may not yet have all the answers, we now know where to look. And that leads to the next question. How do we go further? How do we explore this region more directly? How do we gather more data from beyond the edge of the solar system? To answer the question raised by Voyager 1, we cannot rely on Voyager 1 alone. It is too far, too old, too limited in what it can measure. It has given us something extraordinary, but it cannot give us everything. If we want to understand the interstellar medium in detail, if we want to know whether Voyager 1's anomaly is unique or part of a larger pattern, then we need to go further. We need new missions. And that's exactly what scientists and engineers are beginning to plan. According to studies supported by NASA and the ESA, there are proposals for next-generation interstellar probes, spacecraft designed specifically to travel beyond the heliosphere, carrying more advanced instruments, more powerful communication systems, and a deeper understanding of the environment they will encounter. These missions are not simple extensions of Voyager. They are a new class of exploration, built with the knowledge we have gained over the past decades, including the lessons from Voyager 1. One of the key goals of these future probes is to measure the interstellar medium in greater detail, to map plasma density, to study magnetic field structures, to detect waves and fluctuations in ways Voyager 1 cannot. Because while Voyager 1 has provided valuable data, its instruments were not designed for this purpose. They were designed for planetary exploration. Interstellar space was never the primary objective. Future missions will change that. They will treat interstellar space not as a destination, but as the focus. And that shift in perspective is critical, because it allows scientists to ask new questions, to design experiments specifically aimed at understanding how signals propagate through this environment, how plasma interacts with electromagnetic waves, how magnetic fields influence communication. These are not just theoretical questions, they have practical importance, because as we send spacecraft farther from Earth, communication becomes more challenging. Signals take longer to travel, they weaken, they become more susceptible to interference. Understanding how interstellar space affects those signals will be essential for maintaining reliable communication. And that is where new technology comes in. Future probes may use more advanced encoding techniques, stronger error correction, adaptive communication systems that can adjust based on the environment. Some concepts even explore the use of optical communication using lasers instead of radio waves to transmit data more efficiently across vast distances. These systems could be less affected by certain types of plasma interactions, but they would introduce new challenges of their own, because every new method brings new unknowns, and that is the nature of exploration. Each step forward reveals new complexities, new variables, new questions. Beyond communication, future missions will also aim to provide a more complete picture of the heliosphere itself. Because Voyager 1 has shown that the boundary between the solar system and interstellar space is not as simple as we once believed. It is not a clean line, it is a region, a dynamic interface where solar and interstellar influences interact. To understand that interface, scientists need more data from different locations, different trajectories, different perspectives. This is where missions like an interstellar probe concept become particularly important. A spacecraft launched with the specific goal of reaching the heliopause, quickly equipped with instruments designed to study the transition in detail. Such a mission could provide insights into the structure of the boundary, how it varies over time, how it responds to changes in solar activity, and how it influences the space beyond. In addition to dedicated interstellar probes, other missions will contribute indirectly. Observatories like the James Webb Space Telescope and future space telescopes will continue to study the interstellar medium from a distance. They will observe the distribution of gas and dust, the structure of magnetic fields, the interactions between stars and their environments. These observations will complement the in-situ measurements from spacecraft like Voyager 1 and future probes. Together they will build a more complete understanding of the space between stars. But even with all these plans, one challenge remains: time. Voyager 1 took decades to reach interstellar space. Future missions, even with improved propulsion, will still require many years, perhaps decades. Exploration at this scale is not fast. It is patient, measured, a long conversation between Earth and the distant edges of our solar system. And that means the mystery we are trying to solve will not be resolved overnight. It will unfold gradually as new data arrives, as new missions are launched, as new models are developed. And throughout that process, Voyager 1 will continue to play a role. Even as its power declines, even as its instruments slowly shut down, it will continue to send what it can, for as long as it can, providing a continuous stream of data from a region we have barely begun to understand. And that is what makes it so valuable, because it is not just a relic of past exploration. It is a bridge to the future, a connection between what we have learned and what we still need to discover. And as we prepare for the next generation of missions, one thing becomes clear. Voyager 1 has not just answered questions, it has created them. Questions that will guide exploration for decades to come. Questions that will shape how we design spacecraft, how we interpret signals, how we understand the universe. And all of that leads to a final reflection. Because beyond the science, beyond the engineering, beyond the data, there is something deeper in this story. Something that speaks to our place in the cosmos and to the significance of a small spacecraft drifting alone in the vastness of interstellar space. Somewhere out there, beyond the reach of sunlight, beyond the last influence of our sun, a small machine continues its journey. It does not know where it is going. It does not know what it has found. It simply follows the trajectory it was given nearly half a century ago. And yet Voyager 1 has become something far greater than its creators could have imagined. Not just a spacecraft, but a messenger. A witness, a quiet observer drifting through a region of space that no human has ever seen. And now, a source of a mystery we do not yet fully understand. Its signal still reaches us. Faint, delayed, travelling for more than 20 hours across the vastness of space before touching the antennas of Earth. And when it arrives, it carries with it something unusual, something unexpected, a message that is both familiar and strange. Part of it makes sense, part of it does not. And that contradiction is what makes this story so powerful, because it reminds us of something fundamental. We do not understand everything. Not yet, even after decades of exploration, even after sending machines beyond the planets, even after crossing the boundary of our solar system. There are still places where our knowledge fades, where our models become uncertain, where reality does not fully match expectation. Voyager 1 has reached one of those places, and in doing so it has become a symbol of both our achievements and our limitations. It represents how far we have come. A machine built in the 1970s, still operating billions of kilometers away, still communicating across unimaginable distances. But it also represents how much we still have to learn. Because even with all our technology, all our theories, all our data, we are still surprised, still challenged, still confronted with the questions we cannot yet answer. According to NASA Voyager, 1 will not last forever. Its power is slowly fading. Its instruments will eventually shut down, one by one, until sometime in the coming years it will fall silent. Its final transmission will reach Earth. And then, nothing. Nothing. No more data. No more signals. Only a small, silent object continuing its journey through the galaxy. But even when that happens, its legacy will remain. Because the data it has already sent, including the strange transmission we are trying to understand, will continue to be studied, analysed, reinterpreted, perhaps even re-examined with future technologies that can reveal details we cannot currently see. And that is the nature of exploration. It does not end when a mission ends. It continues in the questions that remain, in the mysteries that are left behind, in the curiosity that drives us to keep searching. Voyager 1's anomaly is one of those mysteries, a signal that does not fully make sense, a puzzle that challenges our understanding, a reminder that even in the most distant reaches of space there are still things we have not yet discovered. And perhaps that is the most important part of this story, not the anomaly itself, not the technical details, but what it represents. Because every time we encounter something we do not understand, we are given a choice. We can ignore it, dismiss it as noise, or we can explore it, study it, let it guide us toward new discoveries. Voyager 1 invites us to choose the second path, to look beyond what we know, to question our assumptions, to explore the unknown, because the universe is not static. It is not fully mapped. It is not completely understood. It is vast, dynamic, filled with complexity and wonder, and somewhere within that vastness, Voyager 1 continues to move, carrying with it a record of humanity, a golden disc filled with the sounds and images from Earth, a message intended for any future discoverer. But perhaps in a way it is also sending a message back to us, not through the contents of that disc, but through its own experience, through the anomalies in its data, through the mystery of its final transmission, a message that says there is more to learn, more to discover, more to understand, and that message, even if we do not yet fully comprehend it, may be the most valuable one of all, because it reminds us why we explore, not just to find answers, but to encounter questions that push us forward, that expand our understanding, that reveal the true depth of the universe we are a part of. And as Voyager 1 continues its silent journey into the darkness, one thing becomes clear. The mystery it leaves behind is not the end of the story. It is the beginning of a new one,